Hello everyone, and welcome to this video. This time we're going to be looking at Schwarzschild geodesics and using a program to plot them. So this video looks at a recently published paper on the ArXiv repository by Cieslik and others. I hope I pronounced that correctly, and my apologies to the authors if I haven't. And it concerns the analytic solutions they derive for the null and time-like geodesics in both the Kerr and Schwarzschild geometries as well. Now, the focus of this particular video is on the Mathematica notebook they developed to plot these geodesics in the Schwarzschild geometry. Now, the paper can be found here, and this link will be included in the description below the video. Now, the Mathematica notebook, that's the original paper, on which they derived the geodesics for the Kerr geometry, but it also, by setting the spin of the black hole to 0, allows you to plot the Schwarzschild geodesics as well. Now, the Mathematica notebook that they provided along with this paper can be found here, and this also will be in the description below the video. Right, so the paper, which can be found here on the ArXiv repository, you go here, this is it. They derive novel analytical solutions describing time-like and null geodesics in the Kerr space-time. Which also, by setting the spin of the black hole to 0, gives you the Schwarzschild case as well. Now, what we're going to do is have a look at the paper just briefly. So let me just get that up. All right, and here we go. The authors, Cieslik, I'm not sure which, Eva Huckman, Patrick Mach. And as I mentioned, they derive time-like and null geodesics in the Kerr space-time, so there's some analytical solutions. The solution are parameterized explicitly in terms of constant of motion, the energy, angular momentum, the Carter constant, and initial coordinates, so initial starting point. I've made a few videos on these. I don't know, 3 or 4 or something, or maybe 3. But this is the one that's going to deal with a particular case where it can be applied to the Schwarzschild geometry, where the Mathematica notebook that accompanies this paper can deal with the Schwarzschild case as well. So I just want to demonstrate some of those. But I just want to point out that the Wolfram Mathematica package will do that. And just a brief overview. I've shown this paper in previous videos as well, but they're going to work with these, the equations of motion, and you have K, the Carter constant here, capital Kappa, and I've gone through this in a previous video, so I won't do it again, but this case, and here's the Carter constant here, in this case, which one was this? Was null geodesics, and Carter constant for the time-like geodesics. And I've covered this in a couple of the previous videos, which you'll see in the Kerr series, the last couple of videos in the Kerr series. I looked at examples of these different types of orbits. All right. So far, that's all well and good. So I'll just go back now. I won't go through that again here. I just want to remind you of this. Now, the Mathematica notebook can be found here, and this link is also included in the description below the video. And to give you an example of the sort of things you can do, let's see how this can be set. So here's the notebook here, you load this. So here's the initial starting point, the azimuthal angle set 0.33 radians. -1 for ER means an inward trajectory, and perhaps I'll move that out of the way. Starting point 25 units away. The polar angle is moving in the positive direction, so that's going down. It initially starts at 0.85 radians. Epsilon, the energy parameter here, the azimuthal angular momentum is set to 3 units. That's in the plane perpendicular to the rotation axis of the black hole. And for the Schwarzschild case, if we set the spin of the black hole to 0, all of these equations can provide the geodesics, can plot the geodesics for the Schwarzschild case. Delta is 0 in this case is for a massless particle, and so an example of the geodesics followed by a massless particle with these initial starting points and energy here. And here we go, we have a plunge orbit. Okay, so I'm going to show a few of these, and you can plot this. Now, this is the Schwarzschild case, not the Kerr case. All right, so let's go back now. And some advice comes with it when you download them from the previously mentioned link. You need to include this file as well. So if I can move that out of the way. Include this file in the same folder from which you run the notebooks. Okay, and that's about it. So there's a demo notebook that goes with it. So whatever you do, if you're going to run the files, say from this folder in front of you that I'm showing on the screen, then you can see I have the Kerr geodesics here, and I have that file I was referring to on the previous slide. All right, now what we're going to do next few slides is I'm just going to show you a few examples of photon orbits plotted using this notebook. So here we go, just move that out of the way. So here we have starting point. The azimuthal angle 0.33 radians, inward trajectory starting at 25 units, polar angle pointing in the positive direction, so going down from above to below. The theta angle, polar angle starting at 0.85 radians. Epsilon parameter is equal to 1, square root of 1 is 1. 0 angular momentum for this massless particle, be it a photon or graviton, what have you. 0 spin, kappa set, the Carter constant set to 12, delta is 0, delta being equal to 0, meaning a massless particle, and it is just a straight trajectory. Well, looking from above and projecting onto the xy plane, it looks like a straight line heading straight for the singularity. Looked at three-dimensionally, this curve in here, this geodesic, here's the geodesic plotted in the 3 spatial dimensions. All right, another example of a plunge orbit. Okay, just varying the parameters a bit. I think what changed there, this time now it has a bit of angular momentum in the positive direction. And so you see a bit more, you see this curve here. So here's a plunge orbit. Okay, here's another one, increase the angular momentum of the photon in the azimuthal direction, that is. And also here, the Carter constant set to 16 units. Next thing, here's a flyby orbit. Okay, starting at 25 units, about over here. And again, moving this way. Stronger angular momentum here, larger value. And here, as you can see, going this way. All right, another plunge orbit. Very low angular momentum, but not quite 0, 0.5. In it goes. What else have we got now? A deflection orbit. Okay, starting much further out now, 200 units out. Polar angle is at pi on 2 minus 0.2 radians, so it's not quite the xy plane, it's a little bit above it. Quite high angular momentum, and then you get this deflection orbit. Okay, another example of deflection orbit. Higher angular momentum. We get this one out here like that. And projected onto the xy plane, it looks like this. Let's keep going. High angular momentum again, higher Carter constant, and you get this orbit. So you can get pretty well what you want. What you won't get, though, are bound orbits, because in the Schwarzschild geometry, there is only one unstable bound orbit, and that's at 1.5 Schwarzschild radii. That's an unstable orbit, and it's the only circular orbit and the only bound orbit you'll get. You won't get bound orbits like you do with massive particles. Okay, so Let's have a look at a few slides now which contain examples of time-like geodesics. The geodesics followed by particles with mass. Remember, massless particles like photons follow null geodesics, and that's what these have been in the last few slides. And now we're going to look at plotting with this notebook, Mathematica notebook. We're going to look at plotting geodesics for particles with mass. Okay, so here we have our starting location. 500 is 0.35 radians, inward trajectory, starting out 25 units. The angle direction is moving in the positive direction, so down if you like, as you'll view from the screen. So from the vertical axis, from the positive direction of vertical axis, you're going down this way. Polar angle starting at pi and 2 minus 0.5 units, so it's not in the xy plane, it's above it, tilted with respect to it. The energy here, this is for a particle with mass, is 1.2. Epsilon is the square root of that. That's the energy parameter. So the particle has some given initial energy. As it's released from its starting location, has 0 angular momentum. Carter constant set to 12. And delta equals 1 means you're dealing with a particle with mass. So it's a straight plunge orbit into the singularity. There we go, like that. Next one. We can get bound orbits with particles with mass in the Schwarzschild geometry, and we can plot those. So here is another version of a plunge orbit. Angular momentum 3.9 units, and we get this. This bit here gets a bit darker because I've plotted it. I've extended the time parameter and plotted over a longer interval, so it repeats itself. Hence, this bit around here gets a bit darker because it's repeated again. It's gone into orbit about that point and stayed there. Next thing, another plunge orbit, starting 25 units out, coming in, plunging into the singularity. Here's a flyby or deflection orbit, and here different parameters. Polar angle set to 0.85 radians. The energy parameter a bit less this time. It's released from rest at a distance of 100 units. The Carter constant set to 100 units, and you can see it just sort of flies this way. All right. Okay, next one. Another deflection orbit. Okay, you get deflection orbit like that, starting out here at 100 units. 5 zeros. The azimuthal angle is set to 0, so it's released, if you like, from the x-axis at 100 units from the origin here, from the singularity, and it's deflected round like this. Quite a high angular momentum, 5 units. Okay, and in 3D it looks like this. Next one. We can plot a bound orbit, as we know that there's orbits precess. In general relativity, orbits precess, so although we have bound orbits, they precess about the singularity here. All right. Inclined at the angle, so it's not in the xy plane. This one is tilted with respect to the xy plane. And here we go again. Another bound orbit, and I think I've got one more to show. Yes, another bound orbit. And one more. Just by altering the angular momentum, altering the Carter constant, altering the inclination of the plane in which the orbit's occurring, gives you these things, and altering the energy too affects it as well. Easy to play with. Now here is an orbit where it does plunge in. So it starts off nearby, about 5 units. So very close to the black hole, very close to the Schwarzschild black hole, but 5 units from it, and then follows this massive curved path before plunging in to the black hole. So there's different things you can do there. So another type of plunge orbit, if you like. And here's another one. You can see it's starting out here and plunging all the way in. Not able to quite escape. The energy wasn't high enough. And here's another one starting out. Here's a deflection orbit like this. And just for interest, I just found this. I'm playing around with it. I found this is just a deflection orbit, but projected onto the XY plane, it gives you this interesting looking shape here. And then you plot it three-dimensionally and it just looks like a deflection orbit. All right, so that was just for interest. In the notebook, you just set these initial starting points and conditions and produce just about any orbit you want. I think that's about it for today. Thank you very much for watching the video. I hope it's helpful, and I'll see you in the next one.